So, hi everyone, this is Abhinav Agrawal from EEEA third year, and I'll be taking through our second project of this session, which is digital to analog converters. But before getting into that project of commonly known as DAC, let us understand what each terms means and some of the basic principles and the blocks behind that. So, yeah. So, First of all, we start with the digital, what is meant by digital and what is meant by analog. So digital is basically representing in zeros and the ones, that is the discrete form. So we do not have level other than 0 or the 1. And basically we have 2 bits. So when we say it is 0 and 1. But in analog, you will see like you will have like the continuous one. So you can say 0 0.2, 0 0.5 and all. So it is the continuous representation. And we go to digital domain because it is easy to store, because in a computer memory you will store it as a bitwise, so it will be 0 1 1 and that things going on. So it is easy to store. And for the analog we need to convert it into discrete form so that machine could understand. So basically one of the example is your DVD players. So if you have the CD that it stores values in the digital form, not in the like suppose I have a mm, CD which consists of some music, so it will be in the digital form, not the pressure waves that has been spoken over there. So that is where it is being converted, and it is easy to process in means like we could mix the signals, and whatever process we want to continue over a digital domain we could do that, which is not the leverage over when go to analog. And it is easy to perform operations like the noise filtering, error removing and all those. So basically we have those RLC circuits and all coming over here. So it is easy to perform in the digital domain as compared to what are in the analog. But in an real world, all the data are analog in analog nature, and that is where we need to convert it from analog to digital. So now, as we are saying, like op-amp is the most basic block which is being used in the DAC or the ADCs. So basically, op-amps are the linear devices that has the properties of nearly the DC amplifications and are being extensively used in the signal conditioning, like the filtering, or to perform mathematical operations like addition, subtraction, integration, and the differentiation. So that is where the word operation means, because it is used to perform many mathematical operations, whereas the amplifier, this is the amplifier. So basically it is a DC amplifier, and this is the block. So basically, we could short it as a voltage amplifying device, which has been used with external feedback components. So basically, we have some feedback components attached from the output towards the input terminals over the plus and minus, and it could be used as feedback so that we could have the desired gain and all. And not going deep over there. So yeah, and if you see like this is a three-terminal device. So basically these two are the inputs, and if you see the sign, this is the plus and this is the minus. So it is the plus one is called the non-inverting input, and those with the mark with minus is inverting input. And these two are the saturation voltage that has been maximum out the voltage that we could get at the output level. Okay, so and the output voltage formulas will be given by the voltage that has been applied at the non-inverting terminal minus the voltage that has been applied at the inverting input multiplied the gain that has been provided over this op-amp. So in ideal case we say like it is tends to infinity, like the gain or the AD, the differential gain which we say tends to infinity, but in ideal condition it is around 10 to power 5 to 10 to power 6. So, like one of the question that arises, like, can we get 100 volt from 1 millivolt? Is it possible? Like, if I say I'll give 10 millivolt, can we get 1000 volt? So practically, it doesn't make sense because you cannot have the infinity gain. So it could only provide up to the saturation voltage that has been output. So even if you provide 1 millivolt and it has gain of around 10 raised to power 5 or 10 raised to power 6, but you not be getting the 100 volt at the output, it will be V saturation, and it is generally plus minus 15 volt. Okay, and it depends on the IC which is being used, and like one of the IC I'll show. Okay, if you see over here, so this is the datasheet for the LM741. This is the most common IC being used. So over here, this is the offset null, that is the plus minus that 15. So over here, that thing. Sorry, no, sorry. Uh, so basically, this is what you guys been reading through. Offset null is like leave it for this time because it is being used to like manage the output. Then we have the inverting input at the second terminal, the non-inverting at the third, and this is the V minus, that is the V saturation which is being used. Then the output at the sixth terminal, and then NC is the no connect. So basically there is no connection made to the IC over here. So that's it. And if you see like the input resistance over here is in the ideal op-amp, we say the input resistance tends to infinity. So basically there is no current going through this terminal over in this path. And because if you see like if you use the KVL, like it's V1 minus V2 divided by the R input. Since R input tends to like in practical it tends to mega ohms. Okay, so and the voltage you are giving is in like volts or the millivolts, so it doesn't have like the current will be in the order of pico amps to nano amperes. So practically we used to take it as 0 amps over here in the inputs, but there are some imperfections, so we'll not go on that part. Then we have the open loop gain, that is the differential gain, and the difference of the voltages, that is VD is equals to V1 minus V2. Okay, so this is the voltage controlled voltage source. And then for the output, so say if I have a source over here, I have some resistance, and I'll be taking the output across this resistor. Okay, so this is the R out, or maybe R load, and this is the R out of op-amp. Okay, so basically if you see to get the proper the output voltage, your R op-amp the output of the op-amp resistance should be as low. So this has been already treated as the 0 or in the order of milli ohms. So that is there. Then yeah. So coming on to our project, that is the DAC. So yeah, this is the example which I have given over here. Like, ever wonder how the music playlist in the digital form are stored in the DVDs, being able to reproduce the sound, that is the analog form from the digital form. So that is where the DAC comes in. So DAC basically takes the digital data and transform it into an analog audio signal, which are then sent to an amplifier so that you could listen to that. So in the similar fashions, DACs are being used in the video encoders, display, motor controls, calibration units, and many more such applications. And in DAC, we have the two types: the binary weighted register, or the it is the one of the type, and second one is the R2R ladder. And I'll be taking you towards the binary weighted registers DAC. So for that, yeah. Okay, so before moving toward that derivation of that circuit, we'll just revise some of the theorems that has been used to like see what that means. So first one is the Kirchhoff's current law. So basically that states that the sum of the current that has been entering in a node is equal to the sum of the current leaving it. So say this is the node and the current I1, I5 and I2 are entering a node. So we'll sum that up, and that should be equal to the current that is being leaving the node, that is the I3 and the I4. So that has been what been stated here. So that is the Kirchhoff's current law. Then in the op-amp, if you say, since I've said like the current on the like the input terminals are treated to be zero because there is much high resistance over here, that is the Ri. So it is the order of the mega ohms. So basically you have that much resistance, so you compare it to nanofarad, like the nanoamps or the picoamps. So it's not a practical sense to like you have some over here as milliamps, the I1 and I2's I3 are in milliamps, and this is in the nanoamperes and picoamperes. So it doesn't make sense to count it as a current. So we generally used to have it as zero. Okay, so I2 is basically been zero, and then so basically whatever the current that has been flowing from the V1, it will go in the RF as well towards the output. Okay, then superposition theorem. So when two or more sources are being present in a circuit, the electrical response across any of the electrical response across the electrical component is basically the algebraic sum of the responses that has been caused considering only the single source at a time. Okay, so if you have remember, like say you have like a circuit over here that has like some V1 voltage source, and then there is another okay, that is having V2. So instead of solving this circuit as a whole at a time, you just take V1 at times, like short circuiting the V2. That is where how the you disconnect the V2, right? So you disconnect it, then suppose I have to take V out across this resistor. Okay, so what you will do, like you will first disconnect the V2, just get the output across this resistor, considering only V1, then disconnect this V1 and have the only the effect of the V2, and then get the output voltage whatever we are going, and then just algebraically sum all those. So I could write V out equals to V out 1 and plus V out 2, right? So that is what the superposition theorem is. And if you see this circuit over here, like for now don't like just consider it as a circuit, and I'll explain why this circuit arises. So you have like four sources for a 4-bit DAC. Okay, so instead of considering all the sources at a time, like while deriving this, we'll consider only one source, like say effect of V1, and then we just short circuit it. So basically short circuiting is like connecting it to ground. Okay, so that is how we'll go on. So if you say like over here, if you see like all the three other sources are being short circuited, and if you see if I have to short circuit, this will go to ground ultimately. So that is where why we have grounded this. Okay, um, then Thevenin's theorem. So basically for an electrical network, a circuit could be represented with an equivalent network that just consists of voltage source and the resistance in a series. So for the previous, so for a complex network, say this is the one of the complex network which you don't know, and this is the V out, like this is the output of the circuit. So basically you could represent this circuit, whatever, like how many sources, and irrespective of that part, you could show it with a voltage source and an equivalent resistance such that and you can connect whatever the say R out. So basically you could connect over here, and this equivalent voltages will be the V Thevenins and the R Thevenin, right? So that is what we being used over here for the derivation as well. So consider it as a circuit. We have the feedback in the form using the R feedback. the resistor being used as a feedback because we have it connected in the output terminal and the input terminal as well. We'll connect the non-inverting terminal to the ground. Okay, and we have four since it's a 4-bit DAC, so we have four sources, and it's 4 bit because we are controlling it for the 4 bits. Say if I make it like we I connect V1 to say 5 volts and others to zeros, so I'll be basically having 100 configurations. Okay, so that is different. Then say if we have V1 equals to 0 and V2 equals to 5 volt and others to be ground as well, then it will be in digital domain, it will be 0100, right? So that is different. So basically we can have the option to change the 4 bits. So that is why 4-bit DAC. So for now we have this circuit, and since the if you remember it, we said it binary weighted resistor. So what that means is we'll have the resistors in the order of 2 raised to power n. Okay, so basically I could choose, since R1 is the first resistor, I could choose say 10k, right? Then my R2 needs to be 2 times of this 10k, so that is 20k. And then R3 is 4 times. Say this, if you see, like it is the 2 to the power 1, 2 to the power 2 basically, so 40k, and this is 2 power 3, so it is 80k. Okay, so for an like n-bit DAC, you need register from R to up to n 2 raised to power n minus 1 R. So that is one of the compulsion of this binary weighted DAC. Okay, and for the unity gain, so basically if you see, like the feedback is in the inverting terminal, and for now you have to just I'll derive, yeah, I'll derive that, but okay, I'll just write out the formula. V out equals to minus of RF divided by like, okay. Okay, suppose this is your circuit, then we could write as V out equals to minus of R feedback divided by the RTH into VTH. Okay, I'll derive that in later part as well, so that's not a problem. But since it's in the inverting terminal, you could like it's the general formula, and you're gonna have it on your 5th sem as well. And when the feedback is on the non-inverting terminal, the formula will be different. So don't generalize it. Okay, and okay, now we're gonna apply the superposition theorem. So basically, we are considering only V1, and we'll short out all those other sources V2, V3, V4. So if you see out this circuit like this, so we have R2 connected to ground, R3 connected to ground, and R4 connected to ground, and we have the V1 over here. So, and if you see by the current division, so this is the VTH. Okay, so the voltage that is across will be the across the R2, R3, R4 in parallel, and R1, right? So equivalent circuit will be like we have V1, we have R1, and we have all those 3 resistors that are being parallel. Okay, so this is what. Yeah. So basically, if we are considering the voltage across this, then you have to say like what will be the voltage across the 3 resistors. So now let us represent as R2, R3, and R4 in parallel to be Z1. Okay, so by current division, we could have Z1 times the V1 divided by the Z1 plus R1. Okay, that is the Thevenin across this. And for the Thevenin, we also disconnect the voltage V1, and we got whatever the resistance across these terminals. So if you see, then R1 also comes in parallel. So Z1 parallel R1. That is the Thevenin. Now we have this circuit ready. So we have Thevenin, Thevenin, RF that is being connected towards from the output terminal to the non-inverting input, and this. So since we have the current equals to 0 and the amplification gain, that is the differential gain which I have said, like it is of the order 10 to the power 5 or 10 to the power 6. So basically the difference in the voltages across both the terminals need to be very less, like of the order micros, right? So instead of thinking on that way, we used to say like it is the virtual, it has been shorted. Both the terminals are being shorted. Okay, so since it's the positive terminal has been attached to ground, so that is what the concept of virtual ground means. So like in the same way, we have this terminal as well to be grounded. Okay, now by using the KCL, like if you used, we have VThevenin over here, we have 0 volt over here. So there will be a current which is VThevenin minus the 0 volt divided by the RThevenin. So whatever current will be flowing over here will go through this path as well. Okay, so now we have 0 volt and the output say V01. So by using the KCL, we could say the V output 1 is equals to minus of R feedback by R Thevenin into V Thevenin of 1. That is what I have said over here as well, right? So now we'll just substitute what the R Thevenins and all. So and the V Thevenin as well, right? So we have V Thevenin over here. So V Thevenin is Z1 into V1 Z1 V1 divided by Z1 plus R1. This is the V Thevenin, and this part is like the RF by R Thevenin, right? So this is the R Thevenin. And now if you see like this Z1 plus R1 will be cancelled out by this, the Z1 will be cancelled out by this. So if you see at the end, you have like the first output voltage as minus of RF by R1. So that is being connected to V1, right? So this is the RF, this is the R1. In the similar fashion, we could say if I disconnect, like say I connect V1 to ground and consider the effect of V2, by similarity, we could say like, okay, the equation will be V out2 equals to minus of RF by R2 into V2, right? So that is what. And for the third output, we have R by R3 in the denominator. For fourth, we have R4. So that is what. Now by superposition, we could say the V out will be the algebraic sum of all those outputs, right? So we have now, since we are talking about DAC, right? So basically we have input in the form of digital domain. So in digital we have only 1 and 0s. So 1 corresponds to say plus 5 volts and 0 corresponds to say 0 volts. Okay, so instead of writing V1, V2, V3 this terms, I could write it as V in, that maybe, and a bit, say B1 or B2. Okay, so if I say B1 equals to 1, then I'll be having it as V in. So say if V1 equals to V in into B1, right? V2 equals to V in into B2. So I could set the value of B1 and B2 and say whichever voltage source is being acting. Okay, so and since it's a weighted resistor, we have R1, R2 equals to 2 times R1, R3 equals to 4 times R1. So we'll just put it over here, and I have considered it as a unity gain. So basically RF equals to R1. Okay, but you could change on that as well. So we have final expression as V out equals to minus of V in times B1 by 1 plus B2 by 2 plus B3 by 4 plus B4 by 8. So that is also in the form of binary. If you see like this 2 raised to power 1, this is 2 raised to power 2, and this is 2 raised to power 3. Okay, so now we have like, if we say we have an input of something like this. Okay, so 0 0 1 1, so we'll get the equivalent if you just put the number like 0 0 1 and 1. So 1 by 4 plus 1 by 8. So that is 3 by 8. So minus V in 3 by 8. That has been here. So in this form, you could get analog values. And to get more on this, like since analog is basically the continuous one, but when we are converting it from digital to analog, we have these samplings over here. So to increase this level, say for 0 to 5 volt, if I say I have to increase the level, I have to increase the number of bits. So basically, instead of going for 4-bit, we have 5-bit, 6 bits going on, so that we could increase on the level of the bits. Okay, so yeah, that's about the explanation part. Now we'll move on to the Simulink to make that. I'll show you this. Yeah, if you could see. So this is the model, and we are going to make from the scratch. So any doubts up to this point? Okay, no doubt is. Okay, so just type out. Create out a blank model. Yeah, just click on the library browser. Search for switch first. Enter and go to Simscape. There you will find a switch. Just drag draw and press Ctrl R to like rotate it. Then copy paste it to 4 since we are using the 4-bit tag. Okay. Now search for resistor. Okay. Just make a connection on that. And then we'll have a voltage source. Okay, I'll do from the library browser. Okay, we have this. Just connect it over here.
Hello again.
Yes, no?
Yeah, they're asking about the second component name.
Second component.
Yeah.
This register.
Yeah. Okay. Good.
Okay. So this is the switch. Go to your like the library browser. Just type out switch. Okay. Hit enter and then just move down to find out the Simscape heading, and you will have the switch over here. And once you have it, press Ctrl R by selecting it so that you could rotate it. Okay, and get this done. Then you have you could search register from here as well. Like first option is your register. Search for DC voltage source. Okay, that's not so problem. Then yeah, okay. Okay, get this PS constant, or you can just type it out so that you could get it easily. And copy paste it to 4 times because you need 4 such blocks. So basically over here we'll give the digital input, that is the whatever 0 or 1. So you'll set this over here. Okay, connections. So this will go to the switch. Then yeah, I have to connect this over here as well. Okay, this as well for this part. Search for operational. Just type it out operational and you will get the first option as op-amp. So add it to your model as well. Okay, we'll just expand it. Okay, max of RF right here, and connect it over here. Then search for ground. You will get as an electrical reference under the simscape. Then function solver. I think it's okay, solver. This solver configuration, just add it to this, and we need one more thing. Okay, type it out Simulink converter and you will get this PS Simulink converter. Okay, so okay, we'll separate this out. Then we have this reference, so we'll need one for this connected to the non-inverting terminal, and copy paste one as well. Okay, then have this to this point, if x equals to 0 to this. Connect the output from the, this is the feedback register you've been using. Then okay, uh, get a display as well. We will need one for the output and 4 for the input. Okay. Okay, and then just connect this to see like whatever the bit you have been setting on. Yeah, so that's it from the side. And a voltage sensor as well. So get a voltage sensor as well and place it in the output. Okay, reference this, and Okay, so I guess hope you guys also made the connection. Mm, okay, so this is the search for the operation and you will get the op-amp. This is the register which is being using. Then this is the PS switch. This is the PS switch. Then this is the DC voltage source. This is the PS constant. This is the display, and you will be needing a PS to Simulink converter over here as well, and four of them here and one of them here. Then this is the solver. Just search for solver and you will get fx equals to 0. Then this is the electrical reference. Search for ground and you will get there. I hope this is the only components that we'll be using. So now we'll set the values for the registers. So say this is the feedback register, right? So we'll set it to 0 0.5, sorry, 5 and change it over here to kilo. Click on OK, and then for this register, say we have 10 kilo, for this 20 kilo ohms, okay, for this 40 kilo ohms, and for this 80 kilo ohms. So yeah, we have this, and then in constant block we'll just change. So let us try with an example of 1011. So this is the one, this is the most significant bit that has been used. One, change it to 0 and remaining to us 1. Okay, so now if you run the simulation, just yeah, so if you see, like it will be something like V in by 2, since we have feedback resistor as 5 ohm, 5 kilo ohm, and that is at 10k. So we have B1 by 1 plus B2 by 2 plus B3 by 4 plus B4 by 8. Okay, and we have set it to, like, this is minus and V out equals to, okay, so we have set it to 1 0 1 1. So you will get it as 8 plus 2 10 11 by 8 times V in is, okay, I've set it to 5 or not, constant say 5. Yeah. So this is the 11 by 8 into 5, and you have minus, so it will be around minus 3 point something. So that is what been over here as well. Yeah. So you could change on those inputs and just see on that. So that is from my side, and we'll now have the question.